Okay. Welcome to this sixth lecture of the subject Object-Oriented Analysis and Design. In today's lecture, we're going to talk about class diagrams and state transition diagrams. Okay. Before that, one important update. I have posted a group list on the eLearn portal, right? So you please log in into the eLearn portal. You will find an Excel sheet uploaded there with the name group list for assignment. Okay, it is divided into 4 sheets. There are 4 sheets, and the groups are divided into sets. So there are set 1 to set 6. Right, and then in each set there are groups. Now it is very important that you please go through that sheet right away just after the lecture and see which set you belong to. In case your name is not there in the group list, please send me a mail. Okay, I seen mail from few students coming in. I will check out and let you know. Some people have posted on the discussion forum that their name is not there. I will do check from there as well, but if you can please mail me, my email ID is given in the slides. Okay, please write a mail to me, mention your name as well as your ID number. Right? Please do write a mail to me. I will check because this is the list of the registered students that I have downloaded from the eLearn portal. So your name should be there. The sets that I have organized the students into are arranged in ascending order of ID number. Right? So there should be no chance that your name is being missed out. Fine. So please get in touch with me in case your name is not there in the list. It is very important. Fine. This is one thing. The second thing is that previously I had posted the syllabus for the mid-semester examination on the portal. We will stick to that syllabus for the examination. There is one point which talks about visibility, right? So that initially I had mentioned it will not be there, but in the previous lecture I said it will be there. So but we will stick to what I had posted on the eLearn portal. So visibility between classes and packages will not be there for the mid-semester examinations, right? So we will today we will I plan to complete the course for mid-semester examination, which is the 2 final topics that are left: state transition diagrams and the class diagrams. Okay, I'll just take up 1 or 2 questions before starting. So, can we do the assignment after mid-semester or makeup? I've not uploaded the assignment as of now. You will be able to see the assignment next week, and I will mention the submission dates. I will try to keep the submission date close to 15th October, right? Another question, last lecture videos are not available. They are available. Please go through the portal. The slides as well as the videos are available. Okay, I think that's it for now. Okay, let's move ahead and let's start with the today's session. So today we are going to talk about state machine diagrams, right? State machine diagrams are also known as state transition diagrams or even state chart diagrams, right? These diagrams illustrate events and states of things, right? We can draw the state machine diagram for a system or even a subsystem or an object of the system. The whole idea is that given a system, if it exists in different states, then this diagram is useful to depict those states of the system or subsystem or the object, right? So it is very important that given a case study, one should be able to find out whether state machine diagram is a good diagram to go about in order to describe this system, right? And this you would be able to understand only if you find out that whether that given system exhibits states, whether the given system exists in different states at different time, right? And this you can eventually and easily find out from the given description of the case study, right? Although we do not expect you to identify, given a case study, whether the state machine diagram would be a suitable diagram, but then in real life, when you go about a case study and you find out that the particular system described in the case study exhibits a stateful behavior, then it is a very good idea to move ahead and draw the state transition diagram for that particular system, right? Your state transition diagram or the state machine diagram helps you to depict the life cycle of an object, right? So how an object moves from one state to another as various events occurs, and there is a transition of the object from one state to another, right? And when I say an object, so the state diagram can be drawn for an object, for a small system, or even for a bigger system, right? So let's move ahead and understand the notations for the state transition diagrams. So the state transition diagram consists of an event, which is a trigger or an occurrence, right? So whenever an event occurs, right, it triggers some transition, and the system moves or the object moves from one state to another, right? What's a state? A state can be described as a condition of an object at any moment in time, right? And how do you describe the condition of an object? The condition would be, say for example, what are the values of the various attributes of that system or object at a particular point of time, right? So whenever we say that the particular system exists in a particular state, right? So in terms of software, it is the values of the various attributes that it possesses, right? So an event triggers the transition of an object or system from one state to another, from one condition to another, right? Okay. And what is a transition? A transition is a relationship between two A transition is a relationship between two states that indicate when an event occurs, the object moves from the prior state to the subsequent state. So transition is the movement of the object or the system from one state to another, right? With these three things in mind, let's see what a state transition diagram looks like. Right? So this is a state transition diagram or a state machine diagram for a telephone system. You can see here there are two states, an ideal state and an active state, right? Some event happens and the system moves from the ideal state to the active state, right? Similarly, there is another event that happens and again the system moves back from the active state to the ideal state, right? So you can consider this as say a simple phone, a landline phone, the kind of phones that we used to have earlier, or we do even have now. So the telephone is placed on a hook, right? It is active, it is not active, it is ideal, but it is not dead, right? So it's in an initial pseudo state. The moment you lift up the hook, right, and if you put it near to your ears, you will hear the dial tone, right? And you will feel that the system has moved from the ideal state to the active state, right? So this is the kind of depiction that a state machine diagram has. Let's move ahead. Let's see the various notations that are used in the state machine diagram, and then we'll see the state machine diagram in elaboration for the telephone system and for one more example. Okay, so let's just start with the notations. Okay, states are shown as rounded rectangles, right? So this is the first important notation that you must note. You must remember. The states are shown as rounded rectangles. Please notice these rounded rectangles are different from the kind of rounded rectangles that exist in an activity diagram, right? So in a hurry, you might end up drawing the rectangles that you usually draw in the activity diagram. It's very important that you get the correct notation and draw the right kind of rounded rectangles, right? So your state is represented with the help of a rounded rectangle. There is an initial pseudo state which is represented with a solid circle, right, which indicates an initial state, right? So as soon as the system starts, we say it's in an initial pseudo state, right? Coming to the next, there is a transition which is shown with the help of arrows labeled with the events. Now if you see this particular transition which moves the system from the ideal state to the active state, there are some labels written on this transition, right? So we'll understand these labels. Before that, this transition ends with an open arrow, right? So another important thing that we usually need to capture is that this transition arrow is an open arrow, right? It is not a solid arrow. Now let's see how the transition is labeled. The first part of the label is the event, right? It shows off hook, right? If you say off hook, this is the event part, followed by a slash, and then we have the transition action, right? Okay, so the first is the event, the off hook is the event which tells that when this event occurs, the transition happens, right? On occurrence of this event, which is off hook, the system moves from ideal state to the active state, and this is the transition action which is taken, right? So it's an action part which is executed, that is a dial tone is played, right? So as soon as the system transits from the ideal to the active state, what you need to do is to play the dial tone, right? So this is the notation that you will need to follow. First write the event followed by a slash and then the transition action. Action is the implementation that has to be done, right? It is the action that has to be implemented when this transition happens, right? Below the label, there is something written here, which is put into square brackets. This is called guard condition, right? It is not necessary that you write it below the label. Below the transition arrow, you can write it anywhere, but it should be along with the transition label, right? This guard condition specifies that this transition will occur only if the guard condition is true. Okay, I repeat, the guard condition specifies a condition, and only if this condition is true will the transition occur, right? Okay, so I'll just repeat once again. I'll take up few more questions that are coming up. This arrow represents the transition. That means the system will move from one state to another. Okay, there is an event. When this event occurs, there is a transition. When the transition happens, right, this is the transition action that has to be executed. Plus, there is a guard condition which, if true, then only the transition will happen, right? If the guard condition is false and the event occurs, still the transition will not happen, right? So this is an important part of the notations of the state transition diagram. I'll just take up a few questions and then move to the next slide. Is today's lecture part of mid-sem syllabus? Yes. This is not for me to check, but for you to check, but it is a part. You should always mention the transition action and the event. Event is something that has occurred due to a stimuli, right, which leads the system move from one state to another, and during this transition, the mentioned transition action needs to be executed. Okay, I think that's it. No more questions. What is the difference between event and action? Event is a trigger which causes the transition to happen. Action is the subsequent action that will be taken when the transition happens, right? You will understand this more when I take up my next example, right? Will the question clearly mention to us that we have to draw the state machine diagram? Yes, the question will clearly mention that you have to draw the state machine diagram. Okay? Okay. Are the labels necessary in the state machine diagrams? Yes, the labels are necessary in the state machine diagram. Okay? Okay. Let's move to my next slide. So before that, I'll just take up one question. So some people are asking that here I have not mentioned an action or a guard condition, right? If there is no action or a guard condition, you will not mention it. But if there is, in order to ensure that there is a completeness in your diagram, do mention as many events and actions and guard conditions as possible, right? Then only your diagram would be complete in all respects. Fine? Okay, let me take up the next slide and then we'll discuss more, right? So there is something called as nested states, right? What do we do? What happens in nested state? A state allows nesting to contain substates, right? A substate inherits the transition of its superstate, right? So if you see, this particular diagram is an elaboration of the previous diagram, right? And the active state, which was here, I'll just go back to the slide. So this active state has been expanded to depict what are the other states inside this active state, right? So this is called nesting of states, right? So this is in a way level 1 diagram, wherein we are depicting the major states that are there, and then in the level 2 you are depicting the elaboration of the important active state. Okay, I will zoom it a little so that we understand this diagram. Okay, let's understand what's happening in this particular diagram. So this is my ideal state, and then it transits to the active state when the transition of hook happens, right? Now what is happening in the active state? The active state again has the initial state, right? And then it starts with the playing dial tone state. Okay, so what's happening? The moment the your phone is off the hook, right, it goes into a state which plays the dial tone. So it's a playing dial tone state, and unless and until you do any stimulus, it remains in that play dial tone state, right? Okay, then what's happening? There's a transition. Okay, what is the transition? That there is a event, right? Not a transition, there is an event. What is the event that happens? That a digit is pressed, right? You can be more elaborate in writing the event. I have just written a digit. You can write it in more elaboration as that digit pressed. Okay, so the event that has occurred is that a digit is pressed, right? What is the action that will be taken? So the digit will be displayed on the small panel that is there on the phone, whatever you have, right? So that you get to see the number that you are dialing in, and the guard condition is that more digits are pending, right? So your phone has an inbuilt system, okay, wherein it is able to calculate if there are more digits pending. Okay, now this is slightly debatable. So depending on the kind of phone, right, this transition would happen. So there are phones which keep track of the number of digits that you have entered, and once it finds that the number of digits entered are as per a mobile number or a landline number, it would automatically go into a connecting state, right? Whereas there are phones wherein you keep on adding more digits, right? And until and unless you press some go button or a dial button, fine, so it goes into the dialing state, right? So it's just an assumption that I have made, that it just calculates itself if more digits are pending, right? And then it loops into the dialing state till more digits are there, right? And once the number of digits is complete, it moves to the connecting state, right? Fine. I'll just pick up a few questions which have come up for this transition. The transition seems to be complicated. The idea is that it is in a dialing state. The moment you press a digit, it goes into a dialing state, and the dial tone also changes, right? So you no longer hear a dial tone, you start hearing your digit beeps, right? And then once the number of digits is entered, which is either calculated by the system itself, or once you press a green button, right, so it moves into the connecting state. until then it remains in a dialing state, right? So I'll just take up a few questions that have come up. Okay. Not able to understand guard condition. The guard condition specifies the condition which, if true, then only the system will transit from state 1 to state 2, right? So there might be a condition which only if true will the transition happen. Even if the event happens, the transition will not happen unless and until the guard condition is true, right? Okay, I think no more questions on this. Uh, there's a question, this diagram flows in an anti-clockwise direction. Is it necessary? No, the direction is not at all important. You can make it move anti-clockwise or clockwise. That is just a layout depiction, right? The guard condition, more digits pending is not clear, right? Okay, I'll just take up this question and describe again. When you dial in a number onto a say a phone, right? So some systems have an inbuilt ideology wherein they calculate the number of digits entered, which should be there, say in a mobile number or in a landline number, right? And the moment that number of digits is done, it starts connecting, right? So this is the ideology with which I have designed this particular state transition diagram, right? If that is not the case in your phone, the other ideology is it takes on taking more digits until and unless the green button is pressed, right? So the current mobile phones, they have a green button, right? A button which has a phone made on it with the green color, right? So the moment the green color is pressed, then it shows that the number of digits or the digits that you wanted to enter have been completed. From your side, you have completely entered the entire phone number, right? And now you want the system to move from dialing to a connecting state, right? So in that case, that will be the trigger, which will be the complete trigger. Okay, and in that case, instead of more digits pending, your guard condition should be till not green button pressed, right? So till not green button pressed, something like that, you continue to be in the dialing state. You read the digits, give a beep for the digit and display the digit. Read the digit whenever it's entered, and till it's not entered, you keep waiting for more digits to enter, right? This is how the system goes from the dialing state and then to the complete state, right? Okay, I think I'll take up more questions later. Let me just move ahead. And then once the system finishes dialing, then it moves to the complete state, right? And then it starts playing the connecting tone, right? And then you would hear some connecting tone on the phone, right? So to some kind of a tone keeps on coming till it keeps on connecting, right? And then when the connection is done, then it moves into a talking state. What is the event? The event is that the connection has been established, right? So the guard conditions connection is established. The event is also that from the other side you get an information that a connection has been established, and the system, your mobile phone or your phone, starts a call timer, right? And then you are in a talking state. The timer continues to increase in number, and then once you are finished talking. Now what happens once you are finished talking? You might press a red button, right? So whenever you are finished talking, you press a red button, which is for disconnection, right? Or there might be a case that your call gets disconnected otherwise, right? In both the condition, the event that occurs is the disconnected event, right? So once you are disconnected, the disconnected event occurs. What you have to do is that the action taken is that stop the call timer, right? And the system moves from talking state to the playing dial tone state. Okay, now this explains the working of a telephone system. The telephone system depicts ideal state and a nested active state, right? It is also important to understand here is that from this active state has 4 sub-states, right? One can transit from any of these 4 sub-states to the ideal state on the on-hook transition. Okay, I repeat, one can transit from any of the 4 sub-states directly to the ideal state on the on-hook transition, right? So if I'm the state where the dial tone is being played, and if I place the phone back on the hook, you are in the ideal state. If my system is in the dialing state, and if I place the telephone back on the hook, you are back into the ideal state, right? Similarly, if you are in the connecting state and you place the system back on the hook, it's an ideal state, right? So from any substate, this transition on hook will lead your system to be in the ideal state. Okay, I'll take up few more questions again and then only I'll move ahead. Guard condition is mandatory in all transitions? No, only if it exists will you specify the guard condition, right? I might have not captured all the guard conditions in this particular diagram. I might have not captured all the actions in this particular diagram, right? So it is very important that you look into the diagram and identify what is missing, what more can be added, right, in order to ensure completeness, right? But of course, you can never reach a the level which you can say that this is the complete or the only correct version of the diagram, right? This is what we discussed earlier also. But the idea is that you should be able to capture the most important states, the most important transitions, and the most important guard conditions, right? And one very important thing, given a case study, there might be some transitions or some guard conditions that you might need to think and assume from your side and then depict it for the given case study, right? Okay, I'll just take up a few more questions. Some people are saying that they are not able to hear me for some moments. I don't know why. I think others are able to hear. Okay. Uh, do we need to mention states and transitions when guard condition is false? I don't understand this question. It is you have to specify the guard condition below the transition, right, along with the transition label. If the guard condition is false, right, your transition will not happen. Okay, if the guard condition is false, your transition will not happen. If the guard condition is true, then only the transition will happen. Right? So this is important to understand that we are specifying guard condition in order to describe additional specification for the transition to happen. Even if the event happens, but if the guard condition is false, then we know that this system will not transit. Okay, I'll give you few examples of systems which exhibit stateful behavior, right? You can go through these examples from the internet, right? So you would find, okay, I need to change the color. Uh, you would find examples of coffee machines. Okay, a coffee machine is a very good example which exhibits of a system which exhibits stateful behavior, right? So it is initially idle, and then on press of a certain button, right? Say for example, on press of a uh, button for dispatch of milk, milk is dispatched, right? Then on once that process is complete, then on button press for say whatever cappuccino or something like that, or maybe hot water, right? So it's a kind of a machine which which depicts stateful behavior, right? So you can go through certain examples of state diagrams for coffee machines. Then you may even find state diagrams for ATMs, right? So ATM also is a kind of a system which depicts stateful behavior, right? And microwaves is another system which depicts stateful behavior, right? And I have one example of telephone here. The other example is of printers, right? So printers is another system which exhibits stateful behavior. So it's like initially the printer is idle. The moment it gets some input, it goes into a ready state or maybe in a printing state. And once it is completed printing, it comes back to the ready state, right? And then there might be a trigger that there is a trigger of there is an event that might occur which tells that the printer is out of ink, right? So then it goes into an out of ink state, and then there might be a case where the printer is out of paper. So there is an event which happens that the printer is out of paper. So then the printer might move into a load paper state or out of paper state, right? So these are some examples of systems which depict stateful behavior and some common uh, state machine diagrams that you would find on the net easily. I'll just take few more questions. Okay, so one person says that there could be a state wherein between connecting and talking, if you are not able to connect to the system, right, it doesn't go into a talking state, but it goes back into a play diatone state, right? So there could be this could be there. So let me see if I can draw. So from the connecting state, there might be a transition to the playing diatone state where the event is not connected, right? So you are not able to connect to the particular caller. Either the particular caller is busy or the connection is not established, right? So there could be a transition from connecting to the playing dial tone state back. Okay, I'll just take up a few more questions. How to handle multiple outcomes of a guard condition? You should design your guard condition in such a way that it results in only true and false. Okay. I do away with so many questions now. I'll take up few more questions later. Fine. Let us move to the next diagram, and then you will understand uh, the state machine diagram in a much better way. Right. So let me just move ahead. This is the exercise. Let us draw the state machine diagram for a stack. Right? So the idea is to draw the state machine diagram for a stack. Right? So all the examples that I had given to you, or I've told you, you can go through are state machine diagrams of systems or subsystems. Right? But initially I even mentioned that the state machine diagram can be drawn for objects as well. Right? And this is one example of a state machine diagram that we will be looking at now, which is for a stack. Right? And I hope everybody understands what a stack is. Right? Okay, so I'll just take you to the diagram and then we'll understand it and I'll explain it. Sorry. Okay, let me zoom this. Okay, so this is the state machine diagram for a stack, right? Let's notice the states that exist in this stack, right? So if you see, there are 3 states a stack might exist in, right? There can be an empty state, there can be a partial full state, or it's a partial empty state or a partial full state, so I name it as a partial state, and there is a full state, right? Okay. Now if you see here on this diagram, the various transitions have elaborate labels, right? And if you see, I have got a few assumptions here. The assumptions are that the top of the stack is initialized to -1. My max is equal to 9, so there can be total of 10 elements moving from 0 to 9. Okay, so there are total of 10 elements. Stack can have 10 elements. So you can restrict yourself to say n, right? So just to make it easy, instead of going for n, I've said that my stack has 10 elements. The max is 9, and the elements move from top moves from 0 to 9, so a total of 10 elements, right? Fine. My initially the top is equal to -1 and my system is empty. My stack is empty. Fine. Now, even before I move ahead, it is very important to understand that the question I gave you was this, right? Draw the state machine diagram for a stack, and this has the underlying assumption that you know what is a stack, you know that a stack has a top, you know that a stack has a maximum number of elements that it can take, right? So please keep this in mind that given a question, there would be a number of assumptions that you might be required to make in order to draw the diagram, right? And this holds true for any kind of diagram that you might get. But your assumptions should be correct, right? And should be within the boundaries of the system itself. Okay? Okay, I'll come back. So this is the initial transition that happens. My top is equal to -1. So from the initial pseudo state, my system starts with the empty state. Fine. I did not label the transitions. I should have done that, but anyways, we can still discuss. So if a push E event occurs, right? If a push E event occurs, that means I'm pushing an element onto my stack, right? What is the action that has to be taken? Top has to be incremented. Top is equal to top plus 1, right? And this guard condition should be true, then only my transition will happen. What is the guard condition? Top is equal to -1, right? So if my top is equal to -1 and a push event occurs, my system moves from empty state to partial state, right? If my system is empty and a push event occurs and my top is equal to -1, right? This is top is actually equal to -1 when the system is empty, when my stack is empty. Then what you have to do, follow this transition path, move the system from empty to the partial state and increment top, right? Additionally, you would see here that there is a loop transition, right? What this loop transition is saying, if on an empty stack a pop occurs, right? My stack is empty and a pop event occurs on the stack. What is the action that has to be taken? An underflow error has to be displayed. Okay, my action would be that an underflow error has occurred. And this transition will happen only when top is equal to -1. That means my system is in an empty state, right? And in this particular kind of a system, there are only two events that are possible. One is the push event and the other is the pop event, right? I hope this everybody knows that on a stack, only two kind of events occur. This is a push, there could be a push event or there could be a pop event, right? So if I am in the empty stack, if this guard condition is true and a push event occurs, transit here. If a pop event occurs, stay here, right? Let's move ahead. I'm in the partial state. Again, in this partial state, two kind of transitions can occur, push and pop, right? Now if a push occurs, okay, and my top is equal to max -1, right? That is, I'm only short of one element to reach a full state, right? In that case, I will increment top and move or transit my system from partial to full state, right? However, if a push event occurs and my top is less than max -1, right? Okay, there I still have space in my stack to push in more elements. I will still remain in the partial state, and hence the loop over this particular transition. Similarly, if I am in the partial state and there is a pop event that occurs, right? So what will happen? I will remove the elements, pop out the elements from this stack, and you will still remain in the partial state till my top is greater than 0, right? There might be a chance that there is only one element in the partial state, right? And a pop event occurs. So what will happen in that case? I will move from partial state to empty state, right? This is a very good example of a state machine diagram to depict the state machine diagram of objects, right? You would rarely find somebody depicting a state machine diagram of a stack, right? But here it is very, very clearly you can understand how a state machine diagram can be depicted. A stack depicts three important states: empty, partial, and full, and only two events are there: push and pop, right? And it is only based on the guard conditions that transition might happen this way or the other way, right? So either you move to the full state or you will move to the empty state depending upon the guard condition, right? And whenever there is a transition, you have to execute the related or the associated transition action, right? I will upload these slides. Please go through this state machine diagram and understand this, and let me know if there are any issues. I'll just take up a few more questions and then we'll take a break. Okay, there's a question, how about the final state? So there might be systems which might have a final state, right, which is depicted as a end state, which uses the symbol of um, one small circle, solid circle with inside a one hollow circle, right? That small symbol which represents the end, right? But in this kind of a system, it's a loop that you are having between the states, right? So it comes back to the empty state. Once initialized, it is there in the empty state, right? You might like to add an end state. You can add an end state if you so desire or if the system so desires. I'll just take a few questions. Why can't the initial value of top be 0? You can take the initial value of top be 0, calculate accordingly. But as far as I know, whenever we implement stack using arrays, right, you initialize the initial index to -1, and as soon as your a number, an object is added to the stack, then you move from 0 to n-1, right? But it's up to you. Will we be given info about states, events, etc. in the exam to draw the state machine diagram? This is what I was trying to explain you. In the previous question, when I said draw the state machine diagram for a stack, you can understand that I have not mentioned anything ahead, right? It's only the stack that I have written, and the rest of the thing is all assumptions, right? So if you might get a system which is very common, say for example an ATM machine. So if I write, please draw the state machine diagram for an ATM machine, there is nothing else that I expect that you can expect me to provide, right? An ATM machine is something that everybody has used. You will need to make the underlying assumptions. What should be the states? What should be the actions? What should be the events, right? Similarly, if I ask you to draw this diagram, same diagram for a printer, right? Or maybe for a coffee machine, or maybe for something else, maybe for a mobile phone, right? So if it is for a very common system which everybody has used, you might not be uh, given any further description in the question itself, right? But assume you will not get a certain system which you would not be used to, right? It would not be that way. And otherwise, if it is for a particular system, then the entire description would be given, but still certain assumptions would be required from your side. Okay, I don't think so. Any more question? I did not get this question. First item, second item. There can be any number of items which might be pushed onto the stack, right? So your stack um, has a space for 9 elements to be pushed, and we refer an element with E, right? So you push E onto a stack. self-state transition are shown as pentagon. Can it be drawn in freehand style? Please, this is not a pentagon that I have tried to draw. It is, when you will draw it with a pencil, it would be like a loop like this. Okay, it's just because I had a only the line tool that was available to me to draw the transition, so I have drawn it using try to draw a loop using that, but otherwise freehand it would be like a loop like this. Okay. Okay, I think I've answered all the questions. Okay, we'll take 5 minutes break here, and we'll come back and take up the class diagrams.